Guys, let me show you why I am the boss. And the time independent Schrödinger equation.
I'm going to show you why the Schrödinger wave equation is the almighty equation. There are two types of Schrödinger wave equation: the time-dependent Schrödinger wave equation, the time-independent Schrödinger wave equation, all gotten from the wave function. Keep my videos very important, because if you look all over YouTube, you will not get an explanation like the one I'm about to give you. Let's go.
So guys, today we're going to be doing quantum mechanics and Schrödinger wave equation. So quantum mechanics. So the topic is Schrödinger wave equation. Schrödinger wave equation. Now, in Schrödinger wave equation, we are considering two types: the time dependent and the time independent. Today we are going to be doing the time independent. Guys, let me show you why I am the boss. Now, the Schrödinger wave equation is telling us about energy. Energy is conserved. We all know that total energy is equal to kinetic energy plus potential energy. So guys, let's go. E equals to kinetic energy plus potential energy. This is equation 1. Guys, I will not be talking much, but kinetic energy is equal to 1 over 2 mv squared. Equation 2. Substitute equation 2 into 1. We have, when we do the substitution, energy is equal to 1 over 2 mv squared plus PE. Now, PE is the potential energy, E is the total energy, and E is the kinetic energy. But momentum equals mass times velocity. We have P for momentum equals mv, equation 4, making V subject of formula. Guys, you know I don't teach with books, so correct me if I'm wrong anywhere. So we have V equals P over M, equation, this is equation 5, or this is equation 4. Now substitute 5 into equation 3 into 3. We have total energy equal to 1 over 2 m. When you have V, you will put P over M, P over M raised to power 2, because V is raised to power 2 here, plus PE. This is equation 6. Now from here we have to do evaluating equation 6. When we evaluate it, more like doing the expansion of equation 6, I don't want stuff to show like this. Okay, so I hope you can see it. I just adjusted it. Total energy equal to 1 over 2 m P raised to power 2 over M raised to power 2 plus PE. So now let's break it down further. E equals M cancel M. You have 1 over 2 m P squared plus PE. You can break this into P. This is equation 7. Now that we have equation 7, there is a law from de Broglie. De Broglie says that the momentum is equal to mv, which is equal to h, which is Planck's constant, over lambda, which is the wavelength. So we have from de Broglie P equal to mv is also equal to h over lambda. Equation 7. De Broglie stated this theory. Now let us substitute P into, this is equation 8, sorry. Let us substitute equation 8 into equation 7. Substituting equation 8 into equation 7. We have, now let's substitute. We have total energy becomes, when we substitute this, you have h squared over lambda squared dot 1 over 2m plus PE. P is the potential energy. This is equation 9. Guys, Schrödinger wave equation is a lot. Now let's go back here. Now that we have this equation, we have that further breakdown. Energy equals h squared, that's Planck's constant, over 2m lambda raised to power 2 plus potential energy. Let's call it equation 10. Making lambda raised to power 2 the subject of formula. Guys, like I told you, I don't teach with a notebook, so you can correct me if you think I'm wrong. First of all, collecting like terms. Now collect like terms. We have h raised to power 2, which is the 2m lambda equals to total energy. This crosses and loses its sign minus PE. This is equation 11. Now our target is to make lambda the subject of formula. So how do we do that? We cross multiply again. When we do the cross multiplication, we have something like this: lambda h squared 2m equals to lambda, then total energy minus PE. This is for people that know how to make subject of formula. Don't forget this. Equation 12. Now, lambda finally becomes, lambda raised to power 2 finally becomes h raised to power 2 over 2m bracket, because this multiplies total energy minus PE. Equation 13. Equation 13 is very important because this is the first stage. Now we have gotten the value of the wavelength. So this is the first stage. Now let's go further. Anything we are doing, we are keeping equation 13. Let me keep equation 13. I hope you can see. Let's keep equation 13 here. Please correct me when I'm wrong. I'm not using a notebook. Lambda raised to power 2 becomes h raised to power 2 over 2m bracket E minus PE. That's equation 13. It will be useful. So guys, take notes. All quantum mechanics students in the university, final year, master's degree, final year physics, third year physics, master's degree, PhD people, this is the explanation, because this explanation is not online. This is a detailed explanation from Choma Oji. So remember that I told you about wave function. Wave functions tells you the position of a particle, and everything about quantum mechanics just tells you that quantum mechanics is all about the probability that a particle or an electron will exist in a particular place. So now let us take the wave function as phi equals a exponential I bracket kx minus wt. This is equation 14. Now this is the standard. You can see that this is the amplitude exponential I, like I said when I was doing the Laplacian function. This is the standard wave equation for finding a particle, where phi is what the wave function, a is what the amplitude, k now is what 2 pi over lambda, yeah, then w is the angular frequency, t is what the time, I is what the complex identity. Take this video to any professor in the world. I've not seen anything like this on YouTube. So keep my videos, guys, keep my videos. Now let's go. We have to find the partial derivative of the wave function. First partial derivatives of the wave function with respect to s, because it is a time independent. So if we talk about time independent, we take the x part of the equation. So time independent for first wave function is, we take this and this for ik, we differentiate this from this, that's how we got ik. Then a exponential I bracket kx minus wt. This is equation 15. Now, but remember that phi equals to a exponential I kw minus wt. Equation 16. Substitute it, guys. Let's go. Substitute 16. Substitute 16 into 15. We have the partial derivative, the first partial derivative, of the wave function, the x, equals, we have that I, k, everything here is phi, so we substitute it back, phi, equation 17. Now you see that this is phi, the wave function. Now taking the second partial derivative of 17, we have second partial derivative of the wave function with respect to x equals, you break that down, I k raised to power 2 because you differentiate the wave function again. So it will be raised to power 2, then that wave function, equation 18. If you don't understand this, write me on YouTube. Okay, I don't, because I don't want the video to be too long, but this video will be too long. So having this equation, we have k here. Okay, now we need equation 13. Watch the way we need equation 13. But k is equal to 2 pi over lambda. That is equation 18. Substitute 18. Substitute 18 into, this is 18, sorry, equation 19. So substitute 19 into 18. If you do that, we have second partial derivative of the wave function over x raised to power 2 equals bracket I raised to power 2, I raised to power 2, then bracket, substitute that 2 pi over lambda raised to power 2 phi. That is equation 19. So let's bring that equation 19 properly. Okay, bringing that equation 19, phi over the x raised to power 2 equals I squared 2 pi over lambda raised to power 2, then the wave function. This is equation 19. Something will happen. Let us expand. Expanding equation 19. To expand equation 19, second partial derivative, the x squared equals, first of all, let us note that identity I raised to power 2 is equal to minus 1 in complex number. Substitute it there. If you note that, let's keep it somewhere. That is not this, the identity I raised to power 2 is equal to minus 1. Note this for complex number. Then we'll put, you say minus 1. Then expanding this, we have 4 pi raised to power 2 over lambda raised to power 2. Then the wave function, equation 20. Remember equation 13. Remember equation 13. The value of lambda already is, but equation 13 says the value of lambda raised to power 2 equals Planck's function over 2m bracket e minus pe. So now substitute this, let's call it equation 13. Substitute equation 13 into equation 20. Let's go, guys. Let's go, guys. Let's go, guys. Let's go. When we do the substitute 13 into equation 20, we have second partial derivative of the wave function, the x is about 2 equals, we want to substitute the value of lambda into this, into equation 20. So we have, first of all, let's break down that equation 20. Minus 4 pi raised to power 2 over lambda raised to power 2 wave function. Of course, you can see where the wave function is coming from. Then we want to substitute this is equation 20. We want to put the value of lambda. You have second partial derivative over the x raised to power 2 equals to minus 4 pi over the value of lambda already, h raised to power 2 over 2m bracket e minus pe. Pe is the potential energy wave function. You can see it. This is equation 21. Now what do? We have to reverse it by doing it well. Second partial derivative of the wave function s raised to power 2 equals minus 4 pi y minus 4 pi raised to power 2 over h square. Then what do we do now? We cross over dot 2m right bracket e minus pe wave function. Equation 22 is getting interesting, guys. Let us do the last and let us get the final equation. The time independent Schrödinger equation. Let's go. Second partial derivative of the wave function dx raised to power 2 equals minus 8 times this. You have 8 pi raised to power 2 over h2, then bracket e minus pe wave function. Equation 23. That is the time independent in the x-axis. Guys, let me blow your mind. Let me blow your mind in three-dimensional coordinates. Let's go. Let me blow your mind now. Let me blow your mind. Guys, let me blow your mind. Now, this is for when we have a particle, an electron here. Let's just say, electron here, this is the y coordinate, this is the x coordinate, and this is the z coordinate. Now, this is the electron. We want to get the three-dimensional, time-independent Schrödinger wave equation. We bring it as, this becomes dx to the power, x to the power, raised to the power 2, plus, we have to add d squared phi over d y raised to the power 2, plus d squared phi over d z raised to the power 2, equal to, whatever we have in the left hand side, we have 8 pi raised to the power 2 over lambda squared, bracket e minus pe. You can see. So now, let us finish everything. Let's scatter everything. So, how do we do that? I'm going to write it a little bit in quanta to equate everything, because energy is quantized. Hence, d squared phi over dx raised to the power 2 plus d squared phi over dy raised to the power 2 plus d squared phi over dz raised to the power 2 plus, because this crosses the equality sign, 8 pi square over h square bracket e minus pe equal to 0. This is the time independent. Guys, let us see it. We need to zoom it. The time independent Schrödinger wave equation in 3 dimensions. Thank you and stay tuned. Next class, see you on YouTube. Share my channel. Thank you.